All right, let's talk about one of the most critical, but maybe most overlooked parts of your computer, the device driver. You've probably heard the term, but it's really the unsung hero that makes everything, just work. So let's dive in.
Seriously, just think about this for a second. You have one version of Windows or one version of macOS, but there are literally millions of different printers, webcams, keyboards, graphics cards, all of it. How in the world does your operating system know how to speak the unique language of every single one of those devices?
Well, without a really smart system, the answer is simple: chaos. It would be an absolute nightmare. Imagine if every time you bought a new mouse, you had to install a whole new, specially made operating system. It would be completely unmanageable.
And that potential for chaos, that gets us right to the core problem that any operating system has to solve. How does a single, central piece of software, the kernel, talk to this constantly changing universe of hardware? It desperately needs a standard way to handle all this complexity without having the instructions for every device in existence baked right into the OS itself.
And the solution, thankfully, is just brilliant. It's so elegant in its simplicity, and it's been the answer for decades, still at the very heart of how our computers work today. And of course, we're talking about the device driver. So what is a driver, really? Well, the best way to picture it is as a black box. The operating system doesn't know what's going on inside that box, and it doesn't care. It just knows it can give the box a standard, simple command, like print this page. The box then takes that command and translates it into the super specific proprietary language that one particular printer needs to hear.
And that right there, that's its main job in a nutshell: abstraction. The whole point of the driver is to hide all the messy, complicated, and unique details of a piece of hardware. It just shows a clean, simple, standard face to the operating system, acting as a perfect buffer between those two very different worlds.
Now here's what makes this whole system so dang flexible: modularity. See, these drivers aren't permanently baked into the operating system. They're like little add-ons, right? Separate pieces of code that can be plugged in to the kernel on the fly whenever they're needed. You plug in a new webcam, boom. The OS finds the right driver, loads it up, and you're good to go. No reboot, nothing. It's just incredibly slick. Okay, so this modular design, it's not just some clever trick. It's actually built on a really deep, really important design philosophy. There's this golden rule that makes the whole thing tick, and it's all about separating two key ideas: mechanism and policy.
This idea is so central. You see it in all the classic texts on how to build operating systems. The core principle is this: a driver's job is to provide the mechanism, but it should never enforce the policy. Okay, so what on earth does that actually mean?
All right, let's break it down. Mechanism is just the what. What can this piece of hardware do? Can this webcam stream in 4K? Yep. Can this printer do double-sided printing? Sure. That's the mechanism. Policy, on the other hand, is the how. How do we use those abilities? Which app gets to use the webcam right now? Who has permission to print to that printer? The driver's job is to stay out of that. It just says, here are all the cool things this hardware can do, and then it gets out of the way.
Here's a classic example to make this super clear. On a lot of systems, there's a graphics server that provides the mechanism. It has the raw power to just draw a window on the screen. That's all it does. But then, a totally separate program, the window manager, handles the policy. It decides where that window goes, what the title bar looks like, and how you can drag it around. Because those two jobs are separate, you can completely change the look and feel of your desktop just by swapping out the window manager, without ever touching the underlying graphics driver.
So this powerful idea, this separation of powers, it's used for all kinds of different hardware. And to manage it all, operating systems, like Linux for example, usually group drivers into about 3 main flavors, basically depending on what kind of data they're designed to handle. Okay, first up, you've got your character drivers. Just think of a continuous stream of data, like text flowing from your keyboard, one character after another. Super simple. Then you have block drivers. This is for stuff like your hard drive. Data isn't a stream, it's chunked up into these fixed-size blocks. And the OS can say, hey, give me block number 5280, and just jump right to it. Totally different. And finally, there are network drivers. These guys are in their own little world. They don't deal with streams or blocks. They deal with packets, little self-contained bundles of data that have a destination address stamped right on them, ready to be fired out onto the network.
So, you might be thinking, okay, this is some pretty low-level geeky stuff. Why does it matter so much? Well, the reason we're digging into this is that this single design decision has had huge consequences for, well, pretty much all of modern computing. It really all comes down to 3 big wins. First, modularity. Because drivers are separate, a company can invent a brand new crazy piece of hardware and just ship a driver for it. They don't have to wait for Microsoft or Apple to update the entire OS. Second, flexibility. Remember mechanism, not policy? This means you and your apps get to decide how to use your hardware's features, not some developer who wrote the driver 5 years ago. And third, security. Creating that clean separation helps contain problems. A buggy driver might crash, but it's way less likely to take your whole system down with it.
And that really brings us to the big takeaway here. This principle, separating the what it can do from how it's used, is just incredibly powerful. It's the very reason our hardware and software worlds have been able to grow so explosively for decades. So it makes you wonder, right? Where else in software today, when we're building web APIs or microservices, could we benefit from getting back to this simple, elegant, and time-tested rule?